Well, okay, let's take a look at this problem. So first look at this. The ring 3 program outputs two sentences and then you input the flag. Note it uses open process to open the current process, obtains a handle, and then attempts to overwrite the right flag to the address of the wrong flag. Then, if the overwrite is successful, the final output should be this right flag. This write process memory overrides the wrong flag into this right flag. If the override succeeds, it should mean it fails. If the override is not successful, then it's successful. So our goal is to make open process not return read permissions, or to make the returned permissions lose write permissions. That is what we call this VM word. Okay, then let's analyze this driver. So for this driver, we see this driver entry coming to the real driver entry. This is a WDF framework. We directly find Darrell driver entry and can discover that this driver entry has a lot of obfuscation applied. Looking at it directly would be very troublesome, therefore here we can consider using emulation. So for emulation, there is a relatively useful tool. That is the KSE project, but this project requires some modification. Here, because this framework can't run the WDF framework, so set the entry point here to the location 10ADE, which is the real driver entry, not the driver entry pointed to by WDF. Okay, let's run it. Here I regenerate 1. Okay, we see above. This is the total execution flow it performed. We copy the entire flow. So first, it called a lot of streamap. For this part, because there's too much, we can consider collapsing it. Good, and then we also remove the corresponding blank lines. replacing blank lines might still need to be done with an editor like VS Code. Good this way. After removing all the blank lines, let's take a look. First here, ZW query system information. That is it. Looked for this 0xb11. 11 is for enumerating system modules. Enumerates system modules, then uses strcmp to query for a certain module here. Actually, students familiar with drivers would know it's usually trying to detect debug modules like kdcom, kdusb, kdnet. Of course, it might also be doing other things we don't know for sure. And then after obtaining it, uses RTL init Unicode string to query for psget process section base address. And this API, actually a quick search, tells us it's used to get the base address of the user mode XC in ring 3. Then afterwards, it read these two things. One is KD Debugger enabled, which mainly determines if the current driver is in debug mode. And then KD debugger not present. If it equals 1, it means not being debugged at the moment, equals 0 means being debugged. This one equals 1 means it is being debugged, equals 0 means it's not being debugged. Then it also read KUSERSHAREDDATA. So this structure is a relatively important one in Windows at the kernel level. It has a fixed base address, should be on the address FFFFF780, and for the offset 2D4, we can check the debugger later to see what content it actually reads. Here pause and directly go to KUSERSHAREDDATA. Find this structure. We locate the offset 2D-far and find it's a KD Debugger enabled field on KUSERSHAREDDATA. These two fields are independent reading. Both at the same time is definitely mainly for comparison. To compare whether it has been modified. Because in some cases, if I hook this enable field, I can change it to the value I want it to read. Here, each read will tell you at which instruction the memory read occurred, and we can also find it through calculation. At the beginning, we can directly print out this driver base. So we can use a calculator to compute the addresses it read. So this is the base address. The instruction corresponding to the first read is here, and 4299 is its offset. We open the driver and find the offset 4299. Then we can see the instruction here, move BL racks. Should be the key instruction indicating that this racks points to the value of its KD Debugger enabled field. We can try it. You can try directly loading this driver. It will definitely blue screen. So I won't demonstrate it here. It will just show you the corresponding situation. Of course, before this, we still need to write a driver to try to intercept the driver. We load. Here, actually, most of the code uses frameworks like driver utils. Here, you can actually find the original source from a URL, and hooks like this, it doesn't actually implement much. Here, it matches the name easydriver, then finds a relatively important location and knobs it out. This is one of our choices. Okay, and then let's look at its subsequent effect. Afterwards, it used an IPI interrupt to execute a function. After executing the function, it exits. Exiting is definitely not what we want to encounter, so we can choose to bypass this IP function search for this function. Here, it will execute the past function, so we don't want it to execute. We comment out these two lines. Here, add another line here. So in the end, we can find that when you don't execute these two API functions, it just creates a callback and then exits. Then let's find this function that creates the callback. So this function that creates the callback can register a handle callback. This handle callback can then control our situation here. The handle permissions written in our ring 3 program above. So since its main validation logic will be done in ring 0, let's find its key points. The first is it will cause a blue screen, right? If we make the read result be 0, no, if we make the read result be 1, what will happen? For example, I replaced the instruction here with 1. Then, let's try it. Okay, let's see. First is enable, then kusershared tab, meaning it didn't read this one again. That is to say, after I patched this, it didn't read the specified location again, indicating this instruction is for reading KD debugger not present. Of course, we still need to pay attention to see what happens after it reads it. Okay, we copy this driver file in. After it comes in, it directly blue screens with code 0x_deadbeef, which is definitely custom. So when we see a blue screen, a function we should think of is mainly keybug checkx. That is the function here. We need to focus on this function. If I knock this function out, make it directly return it won't blue screen. So this is our first idea. Let's restore the snapshot. Okay, first we BP this keybug checkx. We set a breakpoint here. And then copy it in. After running, it will break at this position. At this moment, change its code here to C3, which is the return instruction. Then let it continue. Found it loaded successfully, but at the same time, you'll notice here the debugger has already been detached. It's been detached. One reason for the detachment is mainly because it writes to this flag. It will write to this flag. Once this flag is written to 0, the debugger will immediately disconnect. So this is not what we want. We need to debug it. Okay, and then we still set the breakpoints first. And then, because the first breakpoint will be hit, so we just wait for it to break. Good, and then do the same change it to C3 to prevent blue screen, and then here at the same time we also set a write breakpoint on this KD debugger enabled. There's a flag called KD debugger enabled. See what the issue is. It says it's not aligned. We just need to write one byte. Good, and then we get it. Found that it tried to write at this location. For hardware breakpoints, there's a preceding. It has this action on the previous instruction. So we find this location, it's malloc, because malloc is at plus 0 times 1000. So at the beginning, plus 0 times 3.1, we can find the location of this instruction. Good, and then we decompile the previous instruction. You can see the decompiled previous instruction here. There is a move byte ptr rex 0. Good. We see this rex is 2eb9, and at the same time we find he breakpoint. We just set points to the breakpoint. We just set points to this KD debugger enabled, and then the breakpoint there, which exactly points to rex. So our location here is correct. At the same time, if we just change the code here to NOP, can it successfully bypass this? Anti-debugging. Therefore, the logic for writing our driver here is the same. The logic for writing our driver here is also to find the right location here and override it with NOP. Here, just need to provide this. Good, and then compile this driver. Because at this time it has written successfully, so the debugger will break, still need to restore. But we already know where its location is, which is a relatively big step forward. First copy the driver in. That VM tools sometimes has a few bugs. That's enough. First load our own driver, then load easydriver. So when loading easydriver, it will automatically set a breakpoint for us, which is also convenient for debugging. And then because this is locally compiled by me, it's written by ourselves, so there will be debug symbols here to help with debugging. Here we see the address it outputs is here. So first, we take this KD debugger enabled. No, first find this keybug checkex address and change it to C3. And then we also need to change this IP function to 0. Make it return to prevent it from executing the IP function to perform some blocking operations. Okay, at this point, loaded successfully, and let's see if our debugger is disconnected. Found the debugger here is still detached. Let's look for the reason again. Then let's take another look. I need to first cover the previous two functions with C3. And then let's see if its address has been changed by us. That is the so-called 零乘49 D here. Oh, 零乘4 D 9 E. Just mistyped. First, we set a breakpoint here. Good, when we directly come to this location, we can also see this address. Similarly, come here. Step over, good. Now let's look again. Here it's been noped, which is our expected behavior, and then continue. Continuing still didn't achieve our expected result, and the debugger was detached. Need to restart the snapshot again. This time we need to additionally pay attention to 2 points. 1. Whether there are other places performing this operation on it, or whether the address we found before is correct. Of course, there's also a function called kd-disable-debugger. Just now, probably because we didn't notice this function. And then there's also the ipy function. Also cover it. This way we let it continue again. We can find that the entire debugger runs now. And it frequently outputs process names here. So we consider that when it validates the flag logic, it definitely verifies this name. Therefore, we need to find a way to obtain it. Here, our main method is to look at these important functions it left. One is strncmp. Ultimately, we can confirm it will call this strncmp function to compare. Here we can use the winarc tool. We find this callback type, then this is the address of our callback function. We set a breakpoint on this callback function address. Good, and then it will frequently hit this breakpoint. Afterwards, we set a breakpoint on this strncmp location. Good, after it hits strncmp, let's look at its parameters. Its first parameter is rcx, its lsx. We look at rdx, the second parameter. The second parameter we find points to a checker x, indicating this place is verifying, judging our process name. Then we continue to follow down. course, strncmp itself is not important to us. We just need to know its rex. When rex returns 0, it means the process match is equal, so we need to see its key judgment on rex. Good here, isn't there a test exex? It shows that at this point it has started wanting to make a judgment on our racks, then we follow further. Good here, there is a Jane. So this Jane should jump when not equal, meaning jump when it's not this program. We definitely hope it is this program, that is to say. When checker X is doing the verification, it should go straight down. When not called by checker X, it should jump away. So set a breakpoint here. Then the other two breakpoints, we can remove them. Good, and then we open this checker X. We double click and find it hits. Afterwards, we input a few random flags and find it can also hit. Then this place, it's definitely performing a validation operation, so we can successfully break at its validation operation. Here we can find the result it outputs. In order to know its address, we can open it with x64dbg. Good, and then we see the memory layout. Find its base address. According to IDA, we should be able to know. Where does it get the flag from? It's from this. There should be another parameter here. It's obtained at the offset plus 0 times 3080. We just let it continue. And then we directly do db at this address plus 0 times 3080. Doing db allows us to see this is a flag we input. Then afterwards is the debugging phase when we can track this data. When we can track this data, we can then use dynamic debugging methods to trace the changes of this data. Finally, actually, we come to this code. Let's look. It mainly performs validation through this check flag. and then it performs an input here. This input is actually copy virtual memory, copying it from the user layer buffer to this kernel layer buffer. After copying to the kernel layer buffer, it then uses this kernel layer buffer to perform a check. Ultimately, we just need to keep an eye on this input. We observe how this data changes and can find the final flag. And finally uses mmout to perform a validation. In the end, by repeatedly setting read-write breakpoints on this input, we can easily solve this problem.